Hi, my name is Adrian Prinz. I'm a PhD student in Germany at the Institute for Artificial Intelligence in Medicine. Today, I want to show you my project, which is called Platform Independent, Uncertainty Aware, Joint Genomic Variant and Methylation Calling. Let me start by giving you an explanation what methylation is. Methylation is an epigenetic process in which special enzymes add a methyl group only to specific cytosines in the genome. And these cytosines are only these cytosines that are followed by a guanine, and we call these positions CpG positions. Aberrant methylation can play a big role in a lot of different diseases, and that's why we are very interested in finding methylation in our patient data. Right now, there are a lot of different methylation calling tools available, but they all come with a few problems. The first problem is that they are sequencing platform specific, meaning if you have sequenced your data with Illumina, PacBio, and or Nanopore, for each of these inputs, you need a different methylation calling tool. Another problem is that a lot of these methylation callers are uncertainty unaware. During the process of methylation calling, there are a lot of uncertainties like alignment uncertainty, typing uncertainty, and a lot of these methylation callers don't consider uncertainties at all. And the third problem is that there is no support for joint assessment of multiple related samples. Imagine you have one patient and you take two samples from him or her, like a normal and a tumor sample. Right now, there is no possibility to analyze them both on methylation while considering the relation of this data set. We wanted to have a methylation caller which solved all these problems, and as a starting point, we took Velociraptor. Velociraptor is an already existing Bayesian model for genomic variant calling, and my task was now in this project to extend Velociraptor to also recognize methylation. Let me shortly walk you through the model. We are interested in the methylation rate on one specific CpG position. As an input or as observed data, we get all the reads that are aligned to this CpG position. Our overall goal is now to compute the methylation rate that most probable leads to our observed data, so to our reads aligned to this CpG position. To compute this probability, we need two more probabilities for each read. So for every read, we look at the position of the CpG, and then we compute first the probability that the read is really methylated on this position, and we compute the probability that there is no methylation. But how do we compute these probabilities? This depends on the sequencing platform used. If used PacBio or Nanopore, it's quite easy because they already deliver us all the methylation information we need. We just have to look into the BAM file, and for every read, we find an MM and an ML tag. The MM tag is basically just a list of all the positions of all the methylated Cs, while the ML tag gives each of these methylated Cs a probability, how probable it is that they are in fact methylated. And then all we have to do is just look into the list and compute our probabilities out of it. Quite easy. For Illumina, it's a bit more complex because they don't give us the methylation info right away, but we have to compute them ourselves. We take the unsequenced data and treat them with bisulfite, which basically just transforms all the unmethylated cytosines to thymines, while the methylated cytosines stay cytosines. We then sequence our data with Illumina, of course, and then we can look at all the important Cs which can be methylated at CpG positions. And if our base in our reads is a C, this suggests methylation, while not a C suggests non-methylation. And then we compute the probabilities just out of the base quality, which we get by the aligner of choice. I implemented all this into Velociraptor, so now it is able to recognize methylation, and then we wanted to test it on real-world data. For this, we took the SEEK-C2 study, which is a benchmark study and which gave us 14 benchmark samples of methylation data, and we compute the average over it to get our ground truth. In the next step, we got data sequenced by Illumina, PacBio, and Nanopore and computed with Velociraptor our methylation rates on it, and then compared our results with the ones from the ground truth. And then we repeated this process, but for 6 reference tools we found in the internet for their respective sequencing protocol. All in all, our performance was better in 5 of 6 cases, so we were better on 5 samples, but on the PacBio samples, we were worse than the reference tool. If we look now into the future, we first want to improve our performance on PacBio data so that we are better than all the reference tools. But, and I can't stress this enough, the biggest advantage of ValusRaptor is not that it is better at methylation calling than the reference tools, because they are already quite good. The biggest advantages of ValusRaptor is first, that they are sequencing platform unspecific. Second, that we deal with a lot of uncertainties in our model. And third, ValusRaptor offers a so-called scenario. And with this, now it is possible to jointly call variance and methylation on one or multiple samples. For this, we define a YAML. First, we define our data sets like a normal, a tumor, and a relapse sample, and all their interconnections. And then we can define events where you can really target your variant allele frequencies and your methylation rates of interest on each of these specific data sets you defined before. I'm really looking forward to testing this out because it sounds really interesting to do both at the same time. Thank you very much for your attention. Have a nice day and bye.